What specific problem does ReTool aim to solve in the context of reinforcement learning and reasoning in large language models?
ReTool aims to address the limitations of large language models, LLMs, in performing precise numerical calculations and symbolic manipulations during reasoning tasks. Traditional text-based reasoning methods often lead to ambiguity and compounding errors, particularly in complex mathematical problems. By integrating a code interpreter into the reasoning process, ReTool enables LLMs to execute code in real time, enhancing their ability to validate intermediate steps and expand their solution search space. This framework employs reinforcement learning to teach models optimal strategies for tool usage, allowing them to learn when and how to invoke the code interpreter effectively. Ultimately, ReTool enhances both the reasoning capabilities and training efficiency of LLMs, as evidenced by significant performance improvements on challenging benchmarks like AMY 2024 and AMY 2025.
How does the proposed ReTool framework work? Please illustrate the methodology step by step, focusing on both the cold start data construction and the reinforcement learning phases.
The proposed ReTool framework operates in two primary phases: cold start data construction and reinforcement learning, RL. 1. Cold start data construction. Initially, a high-quality dataset is curated by gathering existing mathematical reasoning data from diverse sources, followed by a dual verification process involving human expert curation and DeepSeek R1 evaluation to filter out invalid data. This results in a robust text-based reasoning dataset denoted as D_init. Subsequently, this dataset is transformed into code-integrated reasoning data, where manual calculation steps are replaced with corresponding code snippets and their execution results using a structured prompt template. A two-stage verification protocol ensures the correctness and format of the generated data, leading to the final dataset, D_C, that captures effective tool usage patterns. 2. Reinforcement learning phase. In this phase, ReTool employs a modified proximal policy optimization (PPO) algorithm to train the model. The policy model collaborates with a code sandbox to generate rollouts that include interleaved real-time code execution. A rule-based accuracy reward system is implemented to guide the model in learning when and how to invoke tools effectively. During training, the model iteratively refines its reasoning strategies based on feedback from the code interpreter, allowing it to develop adaptive tool usage behaviors and enhance its problem-solving capabilities. This dynamic integration of reasoning and executable code ultimately leads to improved performance on mathematical tasks.
Can you provide a simple example that demonstrates how the ReTool framework integrates code execution into the reasoning process? Walk through the main steps of the algorithm using this example.
The ReTool framework integrates code execution into the reasoning process through a structured rollout approach that combines natural language reasoning with real-time code execution. For example, when faced with a mathematical problem, the model first generates a text-based reasoning step until it encounters a point where a code execution is necessary, indicated by a code termination trigger, e.g., less than code greater than . At this point, the generated code snippet is sent to a code sandbox for execution. The sandbox returns the output, which could be either successful results or error messages, and this feedback is then incorporated back into the model's reasoning process, allowing it to continue generating text or producing new code snippets. This iterative cycle enables the model to refine its reasoning and tool usage strategies dynamically, ultimately leading to a more efficient problem-solving approach. The entire process exemplifies how ReTool enhances reasoning by leveraging executable code to replace complex calculations, thereby improving accuracy and efficiency.
What are the theoretical or practical advantages of using ReTool compared to traditional text-based reasoning methods? Discuss specific improvements in terms of accuracy and efficiency.
ReTool offers significant theoretical and practical advantages over traditional text-based reasoning methods by integrating a code interpreter into the reasoning process, which enhances both accuracy and efficiency. Specifically, ReTool achieves a remarkable accuracy of 67.0% on the AMI 2024 benchmark with only 400 training steps, compared to the 40.0% accuracy of the text-based RL baseline that required over 1,000 training steps. This demonstrates that ReTool not only extends the reasoning capabilities of the model, but also enhances training efficiency by reducing the number of required training steps. Additionally, the model's response length is reduced by approximately 40% post-RL training, indicating improved reasoning token efficiency as complex calculations are replaced with concise code snippets. Furthermore, the model exhibits a significant increase in code utilization, with nearly 98% of responses incorporating code by the end of training, showcasing its enhanced strategic tool usage and adaptive capabilities in problem solving.
How was ReTool validated or tested? Describe the experimental design, the datasets utilized, and the benchmarks or metrics used to evaluate its performance.
ReTool was validated through a comprehensive experimental design that involved training and evaluating its performance on the Math Olympiad benchmarks AMI 2024 and AMI 2025. The model was trained using the VERL framework with the PPO reinforcement learning algorithm, employing a cold start supervised fine-tuning phase, followed by a reinforcement learning phase that integrated interleaved code execution. The datasets utilized included a high-quality cold start dataset curated through a dual verification approach, which ensured the inclusion of valid mathematical reasoning data, and the code-integrated reasoning data denoted as D_carbon monoiodide. Performance metrics included accuracy scores on the AMI benchmarks, where ReTool achieved 67.0% accuracy on AMI 2024 and 49.3% on AIME 2025, significantly outperforming the text-based RL baseline, which achieved 40.0% and 36.7% accuracy, respectively. The evaluation involved repeating the test set 32 times to ensure stable results, and comparisons were made against competitive baselines to assess the effectiveness of ReTool's tool-integrated learning approach.
What are some limitations or drawbacks of the ReTool method that you identified? How might these challenges impact the generalizability or applicability of the framework?
The ReTool method, while innovative, has notable limitations that could impact its generalizability and applicability. Firstly, the reliance on a curated cold start dataset for supervised fine-tuning may restrict the model's ability to generalize beyond the specific patterns present in the training data, potentially leading to suboptimal performance in novel problem settings. Additionally, the framework's performance is contingent on the effectiveness of the code interpreter. If the interpreter encounters errors or limitations, it could hinder the model's reasoning process and lead to incorrect outputs. Furthermore, the model's ability to adaptively decide when and how to invoke external tools remains a challenge, as it may still fall back on brittle heuristics in diverse scenarios. Lastly, while the model demonstrates emergent behaviors like self-correction, these capabilities are not explicitly trained, which may limit their reliability and consistency across different tasks. These challenges could restrict the broader applicability of ReTool in real-world applications where diverse and unpredictable problem-solving scenarios are encountered.